Okay, cool. So welcome everyone to our first knowledge share. Micah will join in a bit, but we can still get started here. So I want to begin with showing you guys this slide. So this is usually what we use to describe our entire electrical systems. I made this diagram back in I think it was December when we were sending out our vehicle report, which is something our team has to do as per ASC regulations, have a consistent report of the electrical systems in our car, and especially of our BMS system, which is a safety concern, of course. Instead of looking okay, so I know the first thing you think of when you see this diagram is, wow, it's really colorful, which is true. But I've also been told it's kind of intimidating. And I was thinking it's not the greatest place to start for this knowledge share. So instead, I thought of the best way to go through the electrical systems. And to do so is to mainly address these three questions. So as per our agenda, we'll start with, what do we actually need to drive? How do we become a consumer vehicle? And what makes us a solar car? And answering these three questions really involves defining our electrical systems and how they came to being. Just to know about how our design came about, Midnight Sun is a 30-year-old solar car design team, so the electrical system has always been upgrading through each revision of car. But MS14, our current vehicle, is one of our most consumer-like vehicles, as it's intended to be like a sports sedan kind of model for people to be able to be in and move around in. So there's a lot we have to consider with our car, and that is reflected in our electrical systems. And so by answering these questions, we could really figure out what it is. So this can be as simple as you want, but just so that I'm not the only one talking and I'm not really talking at you, I was thinking we could just answer this together. So what do we actually need to drive? What makes us a car? And please chime in as you feel like, or message in the chat. I can't really see the chat, so James, you'd have to help me. Unless James left.
Yeah, I'll let you know if anything happens in the chat.
Yeah, no, like very simply, like what do we need to drive? What makes us a vehicle? Like
an
electric vehicle.
I think we need motors to drive a car. Does that sound right?
Yeah, we need some sort of motive force. That is correct. Anything else? And you can think of it in terms of both a gas-based vehicle and an EV. So either the Toyota Corolla or the Model 3.
Some sort of energy source?
Yeah, exactly. Yeah. Others? How about while we're on the road? What? I missed that, sorry.
No, I was telling them to participate.
Yeah. How about when we're
not trying to pressure, but
when we're on the road, like what do we need to make sure we are driving safely? Because that is essential. We can't just be given the wheel and do whatever we want, right?
Do we need lights?
Yeah, we need lights. We need indicators. That's correct.
Steering?
Know we're coming. Yeah, we need steering. That's great. We need some sort of driver controls. Okay. Yeah, I think that covers the main ones, besides refueling of some sort, which again just goes to our energy source. We need all those things. So yeah, what I listed out was like energy storage, our motive force, driver control, some way to actually control the vehicle we're driving, way to fill up and regain, safety systems. This is also important because we are going at a velocity, and we have systems in place that have failure points, and we have to think about those when we're designing. And this is essential for driving, so that's what I included here. And lights and indicators, because we can't just be pulling up or being on the road without having obvious ways to show that we are where our path for driving is. So like indicators and lights. So let's talk about our version implemented in our cars for each of these categories. Energy storage. So Micah is the battery lead, and we are working on a main battery pack that consists of lithium-ion cells, I believe around 1,400, no, 900, I forget. But anyways, a pack that will literally be the main source for our vehicle. EVs also have these battery packs, and most commercial EVs, as mentioned in the slide, have about 50 to 100. Our pack only has 11 kilowatt hours. And that really goes to show how important the efficiency of solar car design is, because while we don't have as much storage, we have the same amount of people, but we have to think about both like aerodynamic efficiency, power consumption, and other efficiency factors. And then the pack we use is made of lithium-ion batteries, which have high gravimetric energy density, which I believe just means that they have a high energy density per their weight. So they're powerful, yet relatively light cells. And if you guys are interested in batteries, Micah Black is a great source of both tasks related to the pack and understanding of all the testing that's required to make sure we have a usable and functional pack that is efficient. So we're also having a 101 about batteries specifically later this term. You can check the schedule for that. Right, so our motive force, our motors and motor controllers. We use the WaveSculptor 22 motor controllers and Mitsuba DC brushless motors. So why do we use DC brushless motors? It's actually quite interesting. Most EVs will use AC inductive motors instead, but that's because we use DC brushless because they're slightly more efficient, but they are more expensive. So normal EVs like Teslas will use the less expensive AC inductive motors, but have a good enough feedback loop and a highly sophisticated loop such that they are still pretty efficient. So we also use WaveSculptor 22s, which are our motor controllers. And so these ones are newly purchased for MS14. I believe the firmware implementation has already got off to a good start, so controlling them. And they give us temperature, voltage, current data, as well as rotations like data. So we communicate with them over CAN. And if you notice in the previous electrical diagram, there's a specific CAN bus just for us to talk to our motor controllers. And the board that really ties this all together is motor controller interface. So this board will talk through, will both control the pre-charge circuit needed for the motor controllers, and it will communicate over CAN, be the CAN node that communicates with the motor controllers themselves. So this topic will be discussed way more in depth later on with James.
Yeah, if you don't know what a DC brushless motor is or like what the hell a motor controller is, definitely be explaining that further. There's also a lot of stuff to read on. It's pretty interesting. Mm-hmm. It's usually, you'll see like brushless motors versus brush motors. Brush motors, kind of that. If you know anything about how you generate a force through electricity with the switching, I'm blanking. But like the thing turns, and then when the brushes touch, it kind of flips the electrical field, and that's kind of how you generate force. That's kind of like the brush part of it. You can read about it, but I'll definitely be going more in depth into it.
Yeah, for sure. So driver controls. We have to have some way to interface with the vehicle and make sure we are in control. So the driver controls for our systems, we've divided it up into 3 boards, which are pedal interface, center console, and steering interface. So let's talk a bit about each pedal board. That is controlling the pots that are sitting in the pedals of our car. So this is both the brake and accelerator. It basically is relayed information about the angle of the brake and accelerators, as well as steering angle is another thing we implemented for the pedal board. I think it was just because it was like close enough to the steering system so that we could also get data from there. Also, let me know if there's anything in the chat because I can't really see it. Okay.
I'm just reading Nita's comment in the chat. Just Shmika said pot, that's potentiometer, and basically what that is it's a little knob that you can turn to change the resistance, and so that's how you can kind of like measure a physical angle and give an analog signal for it.
Yeah, cool. Thanks, James and Nita. And then we have steering interface board, which this board, this version is actually from MS-12, the board with the chickens on it. So that's also something cool when you're on hardware and you get to design boards. You can really play around with the silk screens and you can have like fun boards. Anyways, so steering, this is from MS-12. It sat in the off-the-shelf steering wheel, and there was a slot for it to fit in, and that's why you kind of see all these pads. And so it had to have a defined shape, and it got the data from the steering wheel itself, such as the steering stock, which has the indicators, I think high beam indicators, cruise control, and other things that were on the steering stock. So it took a lot of like GPIO and ADC inputs. And then we have center console. I just realized I have a picture of both steering MS-12 and steering MS-14, but that's fine. Center console, it's a board that sits right behind the center console. And what that is basically our system into the infotainment display, as well as all the buttons that are relevant, such as like the power button for the auxiliary pack, or actually just for main functionality, and other center console buttons are other buttons to basically interact with the infotainment display, I believe. I forget if I'm missing something. You can chime in, Micah. I cannot hear you.
There we go. Just the park, drive, reverse, neutral, and
yeah, sorry, all drive modes.
Yeah,
are controlled through that. Yeah. So the shape of the center console, and an image would have really helped here, so my apologies, is that there is a circle cut out just for a fan to cool down the Raspberry Pi sitting behind it, and center console interfaces with this Raspberry Pi, and it's basically our central Pi for both displaying to the infotainment display, which I'll talk about later, as well as doing a lot of the logging that we then send to telemetry. Oh, I can actually see this chat. Okay. Yeah, okay, cool. So all of these, another really important thing about all these boards, and one of the tasks that we mentioned in our stand-up, is looking at the noise sources, because these are very based on the signals and signal integrity we get from all the respective systems. And so we really care about the EMI that affects these boards, and therefore all of them have around the same kind of low-pass filter. Low-pass filter being a filter that will attenuate meaning like stop, I guess, frequencies at a certain point. So any high frequency noise that our low pass filter is designed for will not interfere with our signal integrity, which is very important for these. So yeah, this is our driver control system, and those are the three boards. Okay, so how do we, did I skip slide now? Okay, how do we regain energy? That's our charger and interface. So we use the Alcon charger, part number UHF IP67. And how we interface with it is over CAN bus. So what charger interface does is it talks to the charger, and it gets feedback if the charger is connected. I guess like it also controls the charger relay, which is another isolation mechanism that connects our the charger to the high voltage lines. So it in a sense also regulates the amount of time that charging occurs by disconnecting when necessary. And so another thing to note about our charging is that as an EV, and as per the regulations of the ASC and FSGP, which are American Solar Challenge and Formula Sun Grand Prix respectively, we use the J1772 SAE standard for the connectors. So in like the first image, you can see kind of like the charging port we need to use. And in addition, there is something notable about our charging, which is that during competition, the regulations make sure that there is a charging unit that is always in the car and measures when we're charging to make sure we're not charging, or all our charging is accounted for, because as a solar vehicle, we want to primarily use the sun as our energy source, but we can charge when necessary. So we also use, we also have this charging unit that will be attached or in our car, and it involves using NEMA connectors, I believe. So that's just another thing to note about how charging works. It is regulated, and we want to charge as little as possible, but it does have to exist. So safety is extremely important, especially when you're designing a vehicle. So we have our BMS system, and this is one of the biggest safety concerns is our battery pack. I'm not sure if you guys are familiar with World Solar Challenge, but last competition, there was a horrible incident that occurred in which the battery pack, I wish I had the video here, but a battery pack completely, I think there was like thermal runaway or something, and it like made the car catch on fire, and I think it was within like half an hour, the car was completely gone. Like, luckily the driver got out and it was safe. This is a very, like, you guys should see this video. It's actually easy. Their team just stopped at the side of the road, noticed that the pack was on fire, got out of the car. The car was basically in ashes in like very short amount of time. It was crazy.
They also happened to start a bushfire.
Yes.
Wait, World Solar Challenge is in Australia, right?
Yep.
Yes. So yes, that being said, safety is super important, and there's a bunch of stuff that we do in order to make sure that our battery pack is safe and doesn't explode.
Yeah.
Because there are multiple examples of it happening in solar racing.
This is true, yeah. Okay, so our BMS system consists of these three boards: current sense, AFVs, and carrier. All of them are important, and I guess I could briefly talk about their functions. So current sense is in the high voltage pack to the batteries, and it basically measures the current being drawn from the packs at any given moment. I guess before I explain that, a good thing to note is that there are a bunch of conditions we really have to look for of the state of the battery pack before we induce a BPS, which is our battery protection system. So we have to make sure that the batteries aren't over currenting, over temperature, over voltage, under voltage, and I guess over current in the discharge versus charge directions. Both are important. So current sense, we'll measure both of these things. I mean, by both of these things, I mean both the current, if it was charging / discharging, and it will be our point of contact to carrier for those metrics. So carrier is like the central hub of information. It has its own Raspberry Pi that will be logging all the data it receives from current sense and the AFVs, and it will relay this data over CAN, and again log it on the Raspberry Pi. So I guess we should talk about AFVs now, and those are the analog front-end modules. That's what AFV stands for. And what they measure is they have voltage taps to our cells. Oh, this meeting will end in 10 minutes. By the way, when this ends, just re-click the link. Okay, so Yeah, so they're analog front-end modules, and they will measure the temperature and voltage of the cells to make sure, and this data will then be accumulated to make sure that we aren't over-voltaging or under-voltaging or over-temperaturing. Yeah, and so if any of these faults occur, there are a series of steps that we have to take to make sure we deal with them immediately. And that's where our battery protection system comes into place. So when a fault occurs, the carrier is told to, or the carrier first of all gets all this information about battery faults first. It will then isolate the high voltage relays that connect the pack to the high voltage lines, making sure that the pack is fully isolated. Then our BPS kicks in, and we have BPS strobe lights, and we have BPS indicators on the side of the cards. These are all lights that will essentially tell us that, oh, there is something wrong. We have to stop and fix it. And not only will the lights tell us to stop, but the car will stop because the high is isolated. So there is no motors being powered, and we are going to stop and fix the problem. So this is all very important to the car functionality. And in fact, when we're at competition, there's a week of scrutineering before the competition actually starts, and scrutineering is testing. And one of the main parts of testing is our BMS system and BPS, making sure that if a fault occurs, and they will set it up so that they test each fault, that our BPS goes in when necessary and not when we're perfectly fine for operation. So that is very important, and that is how we deal with safety for the BMS BPS. And then the other part of safety is really our high voltage relays. So all our high voltage loads, they all have to be connected with the relay. And if you're not familiar with what a relay is, it's an electronic switch that has an isolation factor because it's a switch that turns on with the energizing of a coil. So we control the coil and we can control the switch. And the biggest important factor is that if the switch fails at any point, it will always fail open. So that means we are always considering the safety, and all the loads that are high voltage will be isolated in the case of a fault. So making sure we have these relays is very important. Making sure we control them only when turn them on when necessary, and when we're ready to deal with the high voltage component is also necessary. So that is our safety. Also in competition, our safety is that we're like an electric vehicle that we made at the university, you know, so it's not like we have jurisdiction to actually drive wherever we like. So we have a lead car and a chase car that are constantly getting data from our car to make sure we're in good operating conditions and kind of be our strategic front to make sure we aren't being unsafe. So let's continue. So our lights and indicators, that was mentioned before. This is essential for when we're on the road. We need to have lights that will basically be indicators, be brake lights, daily running lights. So that's what DRL stands for. We have I think it's another brake light in the rear, but it's higher position. And then we have our indicator lights, which are amber, 2 on the side, 2 in the front, and then 2 in the rear. And then we have our strobe light, which is needed for the BPS fault. Other indicators we have are the horn. So this is necessary as per regulations as well. And we have our rear, left, and right cameras. So basically, to cut down on the aerodynamic inefficiency of our vehicle, so we don't actually have side mirrors or rear mirror. Instead, we have cameras and our necks. So I'll actually go into this a bit more later, but our design has cameras instead that will look to our left rear, look to our right rear, and look to our center rear. Cool. No, okay. So I guess my next question for you guys to chime in on is, how do we add interface to our 4-person vehicle? The last section was all the things that we really need to be a vehicle. But here, it's more like, what do we need to suit the needs of an actual consumer vehicle. So please chime in. Okay, how about like think about it this way. Like here is a picture of like the inside of a Benz, right? It's like really nice, and it's meant for people. There's on the middle of the dash there's a infotainment system, and there is other things for people like ventilation. I guess if anyone can think of anything. I'm actually blocking this image. Right, there's our data management system, so kind of like telemetry in a way. We're getting feedback from the state of our car with that display. And then this other picture is kind of like what MS-12 looked like. So you can see like the inside. I guess it's kind of biased because we're in the middle of like figuring out problems with the car. But you can see that there is improvement for MS-14 in the way that we interact, I guess, with the passengers in our car. There was the infotainment display, which is kind of nice, but we want to add more, or we want to be, at the end of the day, we want to be as close to a consumer vehicle as possible while considering the efficiency needs of a solar vehicle. So what do we have? Well, we have a driver display. That is actually crucial. This is indicative of the velocity we're going at, the drive mode we're in, the range we have left. So I guess the like gas meter, but for an electric vehicle. We have the infotainment system. So this is how we kind of know the state, the driver state we're in, the consumption, the power consumption at a time scale for all of our systems, and just other infotainment like things. Like for example, in the like Mercedes, you can have like radio on, or you can have your Bluetooth connection. The dash also has like USB chargers, like calling interface, Android Auto, all these things. So there's a lot we can work on in terms of our infotainment system in the car. And then we have to monitor the car's surroundings. So like lots of modern cars have the rear view cam when you're backing up and parking. And so we have to send data. That's also needed for a person vehicle. This is especially for our safety and for just understanding the like statistics of the car. And then ventilation, because this is like an enclosed, the windows don't roll down, the vehicle is closed, and you're only driving in summer in like the heat of like Australia or like Texas, and it gets
Midwest US.
Yeah, in the middle of the US, yep. And it gets crazy hot, so we need driver ventilation. So driver monitoring and driver screen. What it tells us is speed, acceleration, and indication, the mode of drive we're in, the battery/range we really have left, and it sits right behind the wheel. This is a picture from interiors, and I guess this driver monitoring and everything in this picture right here on interiors, this is a very like cross-functional category for interiors and electrical, because we have to make sure we have all the displays set up, as well as the feedback from the displays sent to our Raspberry Pis or our CAN network in some means, so that it could then be sent to telemetry. This is about to end this meeting, so when I cut out, just be ready to re-click the link. Okay, so I'm not sure if we have an odometer kind of function for this. I don't think we will, but that's another thing that driver screens usually have, as in the display behind the dash. So our infotainment display. This image is actually from what our infotainment display looked during FSGP 2019. So it like has our, SSC state of charge. Also, this PowerPoint will be sent to Confluence and uploaded. And at the end, I have an appendix with the acronyms and abbreviations. So hopefully, like Nita and James, the ones you're seeing, you can put to the end of the slide deck as well when you get a chance.